Okay, good morning. Yeah. So welcome back to the class. So we are still on the first set of the slide on logic. Okay. So let me briefly summarize what we have discussed so far. So we have defined some logical operators. So this is the not. This is the and. It looks like an A. Yeah, the capital A, right? And. This is the or. This is what? This is what? Very good. Okay. And we haven't seen these two yet. So we are going to talk about these two today. So this is called imply. We will see imply. And this is like, yeah, we have two bidirectional imply. So we call it if and only if, something like this. Okay. We'll talk about these two today. So some logical operator, they are unary. So you give me a proposition, and then I can apply this operator on that proposition to get the new one. So not is like this. So you have a proposition P, then I can get not of P. So I just need one proposition, and then I can do this. So not of P. And some of the operators, we call it binary operator. So binary operator takes two propositions as the input, and then combine them together to give you a new one. So I have a proposition P, I have a proposition Q, so I can get P and Q, which is a new one. Okay, I can get P over Q. Okay, of course I can get P and P, but it doesn't restrict the meaning of this one. Whenever you see this like an and, we are expecting that you have two propositions, one on the left side and one on the right side, to combine together. Okay, so that's why, because we need two of them, so we call them binary. Okay, binary means two. And then we will look at these two today. We have, okay, and then last time we have also talked about the truth table. So truth table is a way, a very nice way to see what is the effect of the application of each of these operator. So for instance, I have P and Q here. Then by listing out all the possibility that P and Q will take, P may be true, Q may be true, Q may be true, Q may be false, and so on and so forth. There are four combinations here. Then we can write down what happens for this particular proposition. So this one is simple. This is P over Q. So in this case, this will be true, 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 false. Is that okay? Okay, very good. Now, using the truth table, we can easily argue that, okay, so we can use the truth table to help us to count how many binary operator that we can find. So, very good. Okay, very good. Yeah, because there are two choices here, two choices here, two choices here, two choices here. Very good. So there are going to be 16 different binary operators. And then we have seen 1, 2, 3 of them. And some of them are too trivial that we don't discuss. For instance, it can be a case that this is true, 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 true. Okay, P something Q, you give true, 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 true. Then okay, so it looks like it doesn't depend on P over Q, right? So in that case, that operator, maybe you call it always true. So when you see that operator, whatever you are combining, then it gives you a true. So some of them are interesting, some of them are not. So for instance, these are all interesting because by changing the value of P or by changing the value of Q, then you may get a different truth value in the end. Okay, good. And then another very useful thing about the truth table is it can help us to prove equivalence. So equivalence, you have this word, right? Okay. So equal value, so they are equal. So we are trying to prove that in some of the cases, two different propositions will always give you the same value, no matter you insert what is the truth value of P and what is the truth value of Q or whatever. So for instance, I have two propositions here. One is this one. This is not, and then I have a bracket P and Q. So the bracket tells me that we should apply this P and Q first, and then get the result, and then get a not. Is that okay? And then here, and then we have another proposition. This is not P or not Q. Is that okay? Not P or not Q. And then let's say somehow we are suspecting that these two propositions are the same. They are always giving us the same value. So let's try to see if it works, if it is true. Okay, so for instance, I want to get not P and Q. So in the truth table, let us list out all the possibilities of P and Q. In that case, we can determine under each of these possibilities what is the value of this P and Q. So P and Q will be simple. This is something that is basic. So this will be true, false, false, true. True, false, false, false. Is that okay? This is N. Okay? And then this is the negation of this one. Okay, so when it is true, then it should be false. When it is false, it should be true. So we get false, true, true, true. Is that okay? Okay, now this not P, we go back and look at this P. P is true, true, false, false. So this not P will be false, false, true, true. Is that okay? Okay, and similarly, this not Q depends on this column. This is true, false on that side. So this will be false, true, false, true. Is that okay? So far so good, right? And then this is not P or not Q. So not P or not Q, we look at this one and this one. So false or false will give us false. Very good. And then false or true will give us true. True, false, true, and true, true, true. Okay, now we have listed out. So we have used truth table to compute all the different cases, true, 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 false, false, true, false, false, for P and Q. And then we get this column. This column corresponds to what happens on the left-hand side. And then this is the right-hand side equation. And this column corresponds to what is happening on the right-hand side. And then you see that whenever there is a false here, there is a false here. Whenever there is a true here, there is a true here. True will get true, true will get true. So that means what? That means that for these two propositions, they will always agree in the truth value. And so we call them equivalent. Is it okay? So the adjective here is equivalent. Okay? So we call these two equivalent propositions. Okay? That's it. Okay, now, so this is one way that truth table can be applied to solve a problem. We are solving this problem. We don't know whether this is correct or wrong. And now, once we have used the truth table, we are certain that this one is always equal to this one. Okay? Okay? That's good. Okay, so let's try to look at this one, if and only if first. Okay? If and only if. So this is the definition. So we define this operator to have this effect. When P, Q, true, true. True, false, false. False, true, false, 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 true. So what's so special about this? Yeah, what is so special? Okay. So how this looks like you have this side implies this side implies this side. Looks like this. Looks like equal, right? So if you look at the cases where it is equal, whether it is true, so this is the true case, this is another true case, then what we see? We see that this and this are the same. And then this and this are the same. So when the left-hand side and the right-hand side are the same, they have the same truth value, then the result will be true. Otherwise, it is false. Okay? So this gives us some way to memorize this symbol. This symbol means the left-hand side and the right-hand side. If they are equal, then we get a true. Otherwise, we get a false. Okay? And another special thing about this one is, let's recall the exclusive OR. Exclusive OR means exactly one of them is true. Okay, when the two of them, it will be true. Otherwise, it will be false. Is that okay? So if you look at it, then these two are actually complementing each other. Whenever this side is true, this side is false. Whenever this side is false, this side is true. Okay? So immediately we actually have this proven. P if and only if Q will be equivalent to what? Okay, it is equivalent to, we first get P exclusive or Q, and then we take a knot. Okay? Is that okay? Of course, you can also say something like this. On the other hand, you can take a knot of this P exclusive or Q, and then it turns out that it is always equivalent to, this is if and only if, P exclusive or Q. Is that okay? Is that okay? So we use the truth table to observe that these two are correct. And then we get two new equivalences. Okay? Okay, now, another one, okay. So the imply, okay. Imply. So imply is defined like this. So there's no particular reason why we give an operator a particular name, but it's just a definition, okay? So it is defined as true, 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 false, false, true, false, false. Is that okay? So it is defined as this one is true, and this one is false, this one is true, and this one is true. Okay. Okay. So we have 3 truths here and 1 false. Okay, let's take a look of what is the case that it is false. Okay. What is the case that it is false? It is false when the left-hand side, P, is true, but the right-hand side is false. Okay. So this is the only case that we're having the value false. So how do we memorize this one? Or how do we connect this particular symbol? Imply. This is called an imply. Imply to this one. So usually it is like someone saying something conditionally, and then you want to show that he's lying. He's saying something wrong. For instance, let me see. Something. So conditionally, a conditional statement is something like if blah 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 blah, then blah 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 blah. Because under this condition, if something happens, then something will happen. So for instance, if what? So for instance, if today is Monday, then I won't be teaching. Okay, so this is something that I'm trying to say to you. But you can immediately tell me that it is wrong. It is, to our common sense, it is wrong. Because, okay, today is really Monday. So we have a true condition at the left side. It's really Monday. But then, I'm now here teaching this class. What I'm saying was, if this is Monday, I'm not teaching. So you will see that this is actually something wrong. We can prove that I'm wrong if you can find out this happens, if something happens. Okay, if it is Monday, then I'm not teaching. Then no teaching, no class. You can actually show that this is actually wrong, because today is really Monday, and we have a class instead of no class. So for this one, we can easily say that it is a false statement. But on the other hand, if I'm saying that if I'm rich, I will buy you an ice cream. Okay, so okay, but this one, there is a problem. You cannot disprove me because I'm not rich. Okay, so only if I am rich and I do not buy him an ice cream, then I'm making a false claim. But on the other hand, you cannot disprove me. So if I'm rich, I will buy you an ice cream. So you cannot disprove me, so automatically, somehow, you need to believe me. You understand? So so you need to believe me. If I really get rich, then I will buy you an ice cream. Okay, you need to believe me. So this is how this imply operator is very strange. Okay, So when the left-hand side, when this P part, so this is corresponding to if P, then Q. So we will sometimes say it as if P, then Q. So if the P part here is false, we will automatically say P implies Q is a true statement. Is that okay? So no reason, but we have to accept this. On the other hand, another case is if you know that P is already true, then the only way to make this a true statement is you need to have Q to be true. Okay? And this is something that we expect. In a lot of mathematical theorem, for instance, if some theorem is correct, then something must be correct. We usually claim this. So we really need that whenever the left-hand side turns out to be correct, then the right-hand side has to be correct. Okay? But the strange case, or the most important case, is actually these two, because we normally will expect that the P part is true. Okay, so when the P part is true, then the value will depend on the Q part. Okay. On the other hand, this is something we call it special cases or exceptional cases. So when the P part is false, then you need to automatically believe that this is true. Okay. So this is the definition of this imply. Okay. Okay. Now, this imply also we have a very useful tautology. Sorry, not tautology, equivalence for it. So it turns out that if you check not P or Q, they will have the same truth statement here. Now, of course, we can write a truth table to check out this is true, false, true, true. But on the other hand, let us use another way to reason why this is equivalent to P implies Q. Okay, so I'm claiming that P implies Q will always have the same truth value as not P or Q. Okay, let's take a look. Okay, let's focus on, because the easiest way is let us focus on when will it be false on both sides. There's only one case that this is false. Okay, one case that this is false. Which case? It is when P is true, Q is false. So the only case that we get a false is true, false here. Is it okay? This is the only case that we get a false on the left-hand side. All the other cases, we will get a true. Is that okay? How about this one? So on the right-hand side, how do we get a false? We notice that this is an or, right? If something or something, you want to get a false in the end. So how can that happen? False, false. We need this part to be false, and we also need this part to be false. Am I correct? So we have to have P itself to be true to make not P false. Is that okay? And we have to make Q itself false to make this part false. Okay, so this is the only case that not P or Q is false. And this is the only case that P implies Q is false. And the cases are the same. Okay, so we will see that this logical, this proposition is equivalent to this proposition. Is that okay? This English word tautology. Tautology. Tautology is what? Okay, it's a proposition or something that is always true. If a proposition is always true, we call it a tautology. So example. So let's give you an example. So we have a very simple example. So I have a P. Okay, it is a proposition P, and then or not of P. P or not P? P is a proposition. Not P is a proposition. Or together, we combine them together, it is a new proposition. But if you look at it, this proposition is always true. Reason, P is true, then we get a true overall. If P is false, then this side is true, we get a true overall. So this is always true. No matter what value of T or F you fit into this P, it gives you always true. Okay? Okay? And then another English word, okay? Contradiction. Contradiction is the opposite. It is a proposition that is always false. Okay, so in this case, so let's have an example. So this example is also easy. So P and not P. And this is a contradiction. Okay. So always false contradiction. So later we will learn some proving techniques. Some proving techniques called proof by contradiction. So this technique is something that we try to assume something is correct at the beginning. But in the end, you arrive at a contradiction. You arrive at something that is always false. And then the proving technique will then tell us that your beginning assumption, the first assumption that you have made, has to be wrong. Okay. We will talk about this more later, but this contradiction will appear later in the course. Okay? Now, okay, so tautology, we will use a symbol T to represent it because it is always true. Contradiction, we will use a symbol F to represent it because it is always false. And then, okay, so we have mentioned what is equivalent. So let's say we have a proposition P, and then we have a proposition Q. So these are propositions. So we can actually say that we have a definition of the equivalent. So we say P and, this is not the logical and, this is the English and, P and Q. These two are equivalent if what? If they, okay, so this is the English meaning, they agree in the truth value all the time, always. Right? Okay. So this is the definition of equivalent. But in other words, okay, so this is the English meaning. But this is actually the same as saying that P, if and only if Q, is always true, right? Right? Because they agree in the truth value all the time. So when this is true, then this has to be true. When this is false, then it is false, right? So we need to have them to agree in the truth value all the time. And now we have learned a new word, tautology. So actually this one, you can also say that in another way, that P, if and only if Q is a tautology. So okay, so in our textbook, we actually define equivalent as, so when two propositions are equivalent, we actually define it in the textbook as P if and only if Q is a tautology. Okay, but let me make this claim here in the class. What is most important is you understand what is meant by equivalent. The equivalent case is happening when no matter what happens, the left-hand side proposition and the right-hand side proposition, they agree in the truth value. So if you understand this concept, yeah, you don't care about this, you don't care about this, you don't care about this. Is that okay? So they're actually saying the same thing in different way. What is most important is you understand what is happening, and you can explain. Okay, you can explain to your classmates what is going on. So if you can do that, then perfect. You understand what is the concept of equivalence. Okay? Okay? Okay. Okay, so we have seen a lot of equivalence. So here, this is the first one that we proved today, and we have seen more. Actually, there are a couple of logical equivalences that are used again and again, so that people will give it names, and then also it is also useful to memorize them. So I will introduce them to you now. Okay, they are very, very simple.